Today with me I have Wojtek Bracha, who is product manager for the inverters for the EMEA region. How today manufacturers are designing those motors so that they are actually compliant with the eco-design.
Okay, so technology-wise, we have to say that in case of electric motors in recent years, there literally has been no significant breakthrough in terms of our knowledge and the technology that we use. On the other hand, we have to say it clearly that with induction motors we are already reaching some kind of, let's say, glass ceiling if we speak about the efficiency.
The reason is simply the way how they are designed.
Yes,
by
yes,
definition.
yes, yes, that's correct. So again, to speak maybe a little bit more about numbers, as I said, at this moment, so in 2025, the minimum efficiency class depends on the power capacity of the motor, but we are either on minimum IE3 or IE4 level. And from my perspective, this IE4 is already the maximum which can be achieved by induction motors due to, let's say, physics, simply speaking, due to physics law that are applicable to these kind of motors. What does it mean practically for us? That if we want to jump into higher category of efficiency, most probably we will have to utilize the technology of synchronous motors. And here specifically, it's worth to mention two technologies that are available on the market. So one is permanent magnet motors, and the second one are motors which are using the phenomenon of synchronous reluctance. So both of these technologies, they are classified synchronous motors. None of these technologies is in fact developed in recent years. So this is something what is already known for many years. Both of these technologies are right now getting more and more popular, but it's not about any R&D or breakthrough innovations that were done in recent years. This is rather a popularization of some certain technology which is coming from, for example, availability of raw materials, generally decreasing pricing of synchronous motors. But also, if we speak about synchronous reluctance motor technology, we have to say that popularization of this technology is mostly driven by more affordable and smarter drives that can control this kind of motor, because in every case, synchronous reluctance motor, also permanent magnet motor, has to be driven by relatively good and intelligent variable speed drive.
So that's actually a very important topic, I believe, and maybe we can explore it a little bit more. Because yes, the technology itself in the, let's say, how the motors are designed, yes, you're right, there was not like a big breakthrough for the last decade or so. I mean, clearly a lot of this, at least the concepts of the motor design were created a long time ago. And I get the point about, you know, what are some of the factors that are influencing the current change of those motors. Obviously, one of them will be the legislation, right? So it is clear how, you know, the eco-design being implemented stronger and stronger is also affecting this. But you mentioned about the point about the smarter drives and the way how those motors are controlled. And I think it's very important that you explain why this is an issue and how the AC drive is actually making this shift in motor technology to happen.
That's true. So, well, in simple words, if you use unsuitable drive to drive this kind of motor, or also if you do not set it up correctly, frankly speaking, you will not achieve the expected result. And I'm speaking here both about the efficiency, but I'm also speaking about the performance level of the motor, for instance, in terms of torque or generally speed and operation stability. Maybe at this point, this is also necessary to mention that these both technologies, so permanent magnet synchronous motors and synchronous reluctance motors, they have different target applications, because these motors and their nature of operation will differ, especially in the low speed area. So taking this into consideration, we could say that permanent magnet motors, they are maybe more universal to be used in wider scope of applications. So we can use it for both variable torque application like pump and fan, and also for constant torque application like material handling systems, hoist, and so on. But if we speak about synchronous reluctance, these motors, especially when the drive is not capable of doing efficient control and perform auto-tuning very well, then this is very likely that this motor would not achieve full torque, especially in the low speed. So in fact, this makes synchronous reluctance technology rather to be used for application in the variable torque area, so pump, fan, also possibly to compressor, but here it's also a bit tricky because you need to size the motor properly, and also you need to take care very carefully of the proper setup of the motor.
So at any case, it seems like in this new approach, you cannot really disconnect the motor from the drive. So it becomes a setup that only if it's selected and installed properly, only then you are getting these results in terms of energy saving, right?
That's correct. Of course, there are technologies already and solutions available on the market that can increase the probability that you will do it correctly, or it will reduce the risk that you do it improperly.
Like the auto-tuning you mentioned.
Specifically, I would name here auto-tuning, correct auto-detection of constant parameters of the motor, and so on. So the key point should be that you can employ to the task the most advanced, technologically the most advanced and the most efficient motor, but if you do the tuning, if you do the setup of the drive parameters improperly, then you will not achieve the expected result. In bad case scenario, it can even have worse efficiency than the induction motor. So at the end, you do not reach your goal. So here we should be careful.
Okay, so let's try to summarize this point about different technologies, not only for motors, but also for the drive, as you just explained, and all of the impact of this selection on the energy efficiency classification and so on. So you mentioned that in most cases the induction motors cannot achieve anything more than IE4, but on the other hand it seems IE4 could be efficient for the time being in the industry. So what is your recommendation? I mean, would you always, looking at the future application, but also like brownfield application where you want to replace the technology to make the production more efficient, would you always recommend the synchronous motors, or would you still keep the high efficient induction motors in place?
Well, so the rule, when we are speaking about efficiency classes, the rule is simple. The higher number you have, the better efficiency class. So in fact, the higher number you have, the less energy should your motor consume. So IE4 is better than IE3, IE5 is better than IE4. As we mentioned, for induction motor, so we can say very traditional and widely used technology, more or less the glass ceiling is IE4 level. It again depends maybe on the power capacity of the motor and the scope that we are discussing, but as a rule of thumb, we could say that IE4 is the maximum. Now let me jump for a second to the explanation what differs synchronous motor from asynchronous motor. So there is one fundamental difference that we have in terms of, let's say, the technology and also phenomena that are present inside of the motor. So when we speak about synchronous motors technology, they have one distinct advantage over induction motor, which is no losses on the secondary side. Traditional induction motor, it has secondary winding, and when the motor is operating, there is a voltage which is induced in this secondary winding. Therefore, the current is flowing, so we have a heat loss on this secondary side. Synchronous motors, if it's a permanent magnet motor, then we have permanent magnets. If it's a synchronous reluctance, there is a different phenomenon of reluctance is used in such motor. But generally, different physics phenomenon are used to generate magnetic field inside of these motors. So what is the result? In case of synchronous motor, if you do not have these losses on the secondary side, because there is no secondary side winding, automatically you reduce between, again, it depends on the power capacity, but you reduce your losses between 15 to 25%. And just resigning from secondary winding allows you to jump at minimum one class up in the energy efficiency classification.
It's that simple.
Well, it sounds simple. Yeah. As I said, the technology right now, due to different factors, is getting more and more accessible. Therefore, overall, globally, the usage of permanent magnet motors is growing faster than induction motors. So it means that the technology is getting more and more popular.
Mm-hmm. Looking for any type of future application, would you say that then the ultimate goal is to reach IE5?
Well, so from international standard classification, at this moment, IE5 is the highest officially classified level. And each power capacity and each, let's say, construction of the motor, by this I mean rated speed, has some minimum efficiency requirements. But at this moment, there are already undergoing some consultation about future efficiency classes. So going back in time, when the ISO standard for efficiency classification was implemented, at that time I think we had IE1, IE2 and IE3 classified, then IE4 and IE5 were added, and in the future we should also expect that higher efficiency classes will be added. So most probably in the new version of the standard there will be also IE6 and IE7. Maybe at this point we should also mention that some manufacturers on the market, they already announced their motors to be IE6 or even IE7. So we need to clarify that at this moment there are no official minimum requirements for IE6 or IE7 efficiency class. However, we can do some hypothetical calculation, knowing that in the past there were some certain differences between each class. So between classes, normally the losses were reduced between 15 to 20%. So using this assumption, we can hypothetically estimate what will be the minimum efficiency class for IE6 motors in the future and IE7 motors. And somehow we can risk, let's say, classification of future motors according to these kind of assumptions. However, as long as this is not defined by international standards, this is all the time just hypothetical assumption that the motor is in some certain class. But answering your question, yes, we can expect that in future more demanding classes, more efficient classes will be also standardized. Actually, I have to say that we also made this kind of hypothetical calculation inside of Mitsubishi Electric, and one of our findings was that if we apply this rule that each next more demanding class has 20% smaller losses compared to the previous one, it would also allow us to classify our EMEA motors, so patented Mitsubishi Electric technology, in either IE6 or IE7, dependent on the power capacity of certain motor.
But let's stay with the existing classification that was already defined, and let's talk about the actual numbers that allow us to, or the manufacturing companies to take this kind of investment decisions. So how important it is to move from one class to another in terms of the actual savings and effectiveness of the production process?
Okay, so let me again try to quantify it. If we are speaking about motors in low to mid power range, so let's say up to 7.5 kilowatt, the difference between minimum efficiency class, which is IE3, and IE5 motor is on the level of 5 to 6%. So this is in fact translating to huge operational savings. If we are speaking about an application which is not running in intermittent duty cycle, we would be typically speaking about payback time between 2 to 3 years again, it depends on several factors. I would say that normally when we are doing this kind of calculation, we are doing this according to some reference conditions, and in our case, the reference condition that we are using is two-shift operation, so 16 hours per day, with average load factor of 70%. And if we are speaking about this kind of application, typically the cost of the energy which is consumed by the motor is between 3 to 5 times the initial purchase cost of the motor. It means that this 5-6% of efficiency difference between IE3 and IE5 class is turning into real savings when we speak about OPEX, so operational cost of the manufacturing site. From the total cost of ownership, this is an extremely important decision, whether we choose the motor which has minimum efficiency allowed on the market, so IE3, or we aim towards more efficient motors that are already available on the market. Number-wise, so the 7.5 kilowatt motor working in this reference condition which I mentioned before, so 16 hours per day, 70% average load factor. If you choose IE5, it saves almost 2 megawatt hour per year compared to IE3 motor. So this can turn easily to 300 to 400 euros in OPEX for your company just by single motor. And additionally, on the top of that, there is 600 kilogram less CO2 emitted to the surrounding, to the environment. So in fact, apart from your wallet, this is also a relief for your scope 2 emission, which you declare in your yearly sustainability report. Similar effects, also very good to speak about numbers, you can have when you do the retrofit of the motor. So for instance, 2.2 kilowatt motor, when you do the retrofit from IE1 to IE5, this can, in the same working condition, this can potentially bring you 1.5 megawatt hour saving per year, which is also equivalent to 450 kilogram of CO2 emitted to the surrounding. And actually, this case of retrofitting IE1 motor is not very unusual, because typically IE1 motors were used before 2016 because of the eco-design directive. After 2016, it was moved to higher classes. So if you have motors or lines in your factory that were installed before 2016, most probably they will be still running on IE1 motors. Last thing, which also should be considered, is that anyway the lifetime of these motors is coming to an end. So right now, very likely that you can be in a position to decide right now to retrofit these IE1 motors to IE3, or to install already future-proof solution, which is IE5, and have, of course, substantial energy saving, therefore reduction of operating expenses and CO2 emission.
What you explained so far, I think that I think it was an important point of conversation to talk about this kind of general conditions that many factories find themselves at, right? So a lot of motors that either way will require retrofitting, and then it's a very important decision whether you should already be looking at the most efficient replacement, or you can somehow maintain the current minimum level defined by eco-design. And this is the general situation. I think it is important to mention, but then we can go into details. And I mean, every single drive in the factory might have a little bit different operating conditions, and of course they are serving different purposes in the industry. So I think it's also important to speak about like energy efficiency under like a varying loads, right? Because not always the drive will be working with the, let's say, the most optimal load, right? And it is quite common that if you are operating under the normal load or above it, of course, the energy efficiency drops. So what is the status then of this situation with the new synchronous motors?
So that's an excellent point. Actually, the value which I mentioned before, so 5 to 6% difference between i3 and i5 class stands for the rated efficiency. So the rated efficiency of motors, maybe not typically, but as the standard is defining, this is measured at the rated working point. So 100% load and 100% speed. But that's true that in fact motors are almost never operating in this rated point condition. So typically, well, especially if you drive the motor with variable frequency drive, the speed is not very it is not very common that the speed will be 50 hertz, so rated speed of the motor, but also in terms of load. And actually, this is a kind of advantage, another advantage of synchronous motors. The further you move from the rated operating condition, the bigger advantage of synchronous motor efficiency over the traditional induction motor we have. So if at the rated working point advantage of synchronous motor is on the level of 5%, it turns out that when you move, for example, to partial load operation like 60%, difference in the efficiency can reach even 7 to 10%.
And I guess this is rather hard to estimate, right? Because those are the conditions that are probably not that easy to emulate, let's say. But would you say that we already have some specific examples where this actually, when you put together, the measuring equipment and then you confirm, how the new application behaves comparing to the old one before the retrofit? Is this something that you already see in the market?
Well, so this is also a very good point and very good question, because so far, let's say I was presenting the theoretical difference between some certain classes, and we were speaking about theoretical values. What I can disclose is that recently, 1 to 2 months ago, started a kind of research with one of our customers, which is a very big manufacturing site. And specifically in this plant, we are testing different scenarios and solutions. At one of the applications, which is a conveyor line working in the company Intralogistics, we have replaced together with the customer old i1 motor, and we installed completely new solution based on our EMEA, so i5 motor. At this moment, I hope this will become public and we can present it in the future as a kind of, let's say, reference or case study to also educate other customers. As for this moment, after the measurement of the energy consumption on the old motor and then after the replacement to the new one, it turns out that the estimated annual savings are on the level of 1.5 megawatt hour per year.
And that
was 1.5 kilowatt motor. So more or less this is matching the calculation which I was doing before.
And this is the saving that is possible only with the motor replacement.
In this specific application, we replaced the complete gear motor, and the area of mechanical transmission system is also quite interesting, especially that so far AC drive is the regulated area. Electric motors are also regulated by the Eco-Design Directive, but there is also relatively big potential in optimization of the mechanical transmission systems.
Yeah, I think there is many things that are in this whole discussion that, in my opinion, would actually require more details, and probably you could give us some detailed explanation on a couple of those points. And maybe this actually is something it can happen. So maybe we can actually organize another discussion, maybe going into details of maybe the whole system approach and details on how the mechanics is also involved in that. I think for today we can conclude with basically with the learning that to achieve the most energy saving in the drive applications in the industry, I think that the proper combination of the variable drives and the high efficient motors is bringing the most savings, right? So making the right selection of the high efficient motor, using a proper drive to steer the motor. Those are the actions that are, let's say, the most impactful when it comes to the drive systems in manufacturing. And I think that this should be our conclusion. So as a summary of this discussion today, because you made a couple of great points, but as a summary, maybe you can give us some final tips on this topic. So energy saving in the manufacturing process.
When it comes to electric drive systems, two things that we mentioned. So first of all, you should adopt variable speed drives technology wherever it's possible and wherever it makes sense. Specifically, we are, in terms of energy saving, speaking here about pumps and fans applications. So this would be my primary recommendation. Second, as you mentioned, choosing consciously high efficiency technology. I would say that the third, let's say, step or third area where we can also put our attention is that we should make sure that the infrastructure that is already working in our site is correctly parameterized and set up. By this I mean that many or majority drives on the market, they are equipped with so-called energy saving mode, which can significantly save the energy in variable torque applications, so pump and fan. But this is very likely that these drives are not set up in this control mode. Very often this is one of the improvements that you can do without having any capital investments. It just requires man-hour of your maintenance or engineering team. And by this you can make sure that the drive which is installed in these variable torque applications, they are running at optimum efficiency. Actually, if you are using Mitsubishi Electric drives, energy saving mode is not the most optimum one. You should set up, if it's available in the drive series that you are using, you should set up optimum excitation control. So this is one of, let's say, superiorities of our drives compared to other commodity drives that are available on the market, that we have this special mode which is allowing to have even more energy saving compared to the traditional energy saving modes, which are available in most devices on the market. My number 4 recommendation would be to take a look at the drive system holistically. So I would also include to this analysis of efficiency mechanical transmission systems, specifically gearboxes. So one of, let's say, conscious choices would be to resign from using worm type gearboxes because they tend to have very low efficiency. So by having this technology installed, you really waste a lot of energy because of the mechanical friction and resistance inside of the gearbox. Instead of this, we should go to high efficiency technologies like helical bevel gearboxes. And number 5 would be to identify places where we are right now losing energy, but we could possibly regenerate it. So here specifically, I would name, for example, vertical transport systems like hoists and cranes, various kinds of elevators, where typically the energy is dissipated, let's say braking energy is dissipated at braking resistors. And if this kind of application is working in a repeatable duty cycle, then very likely that it makes sense to install regenerative drive or regenerative converter in this case and regenerate this energy instead of just dissipating this on the braking resistor.
Perfect. And I think that each of those topics could be another conversation point. So thank you for all of those details. And I think that, we looked also from the technical perspective, but also how this actually affects the business outcomes and so on. So thank you very much for being here. And I'm pretty sure we will meet again.
So I will be very happy to discuss all of these aspects next time with you in details. Thank you very much.